All right, so we've started the pre-AP Chem Unit 2 review, test review. So my goal is to go through the essential skills, and I'm hoping that you guys will get on and post some questions. If not, that's fine. We'll just have this be a review of those things and kind of what you might expect on the test. So as you guys start joining and start putting up questions, I thought I would just go ahead and get started. I have the assignment sheet. Where is it? I had it a second ago. Oh, there it is. Oh, good grief. Okay. So let me share that screen with you then. And that way we're looking at it together. So you can see here, there are 4 essential skills that you'll be tested on. The first one is calculate the percent composition of an element in a compound. The second one is to determine the empirical formula of a compound. The third one is to determine the molecular formula of a compound. And the fourth one is to identify the trend of the different trends of the periodic table for ionization energy, electronegativity, and atomic radii. Now, we didn't do any additional work in that. I just want you to go back and look at your worksheets and such from the periodic trends unit, the periodic table unit, and we'll use those as our basis for what I'm going to draw questions from. But I am going to go through the wording of how I would expect you to word it. So it very much more closely to what we talked about in class. And so for those of you that hopefully will remember, otherwise this will be a very good time to review. All right, well, let's go through some problems. I have some examples that I'd like to show you guys. Let's go to my Bamboo tablet. All right. And I'm going to keep looking for your questions on the Q&A app, which may or may not show up. All right. So, as I said before, we have essential skill number 1. Essential skill number 1, which is percent composition. Okay. So let's do something really easy to begin with, and then from there we can do a little bit harder problem, and that'll just lead us into some other types of problems. So a simple one would be, what is percent carbon in carbon dioxide, CO2? So what you have to do is you have to get the mass of the carbon. So carbon equals 12.01 grams per mole, and the oxygen is equal to 16.00 grams per mole. And I really want to emphasize that you go out to 2 decimal places. And when you add it up together with 2 oxygens and 1 carbon, you get 44.01 grams per mole. Okay, and if we want to know what the carbon is, then we would just say 12.01 divided by 44.01 times 100 is equal to 27.29%. Well, to be honest with you, I'm pretty sure that that's what that is, but I should do a quick calculation. 12.01 divided by 44.01. Yes. Times 100, and it's 27.289. That rounds to 27.29%. And all that is the amount of carbon in carbon dioxide. Okay, it's sort of like saying, in our class, how many boys, what percentage of the class are boys? And if we have 34 students in the class and 17 of them are boys, 17 divided by 34 is 50%, times 100 is 50%. So very simple. Let's do a little bit more complicated one, what if we had, so what is carbon in, where is it? C2H5NO, okay? And in some problems, you know, I might have you all four of them, carbon, hydrogen, nitrogen, and oxygen. But I'm just gonna do carbon right now to save time. We know that carbon is 12.01. We know hydrogen is 1.01. We know nitrogen is 14.01. And we know oxygen is 16.00. So we add them all together. So C out of C2H5NO is equal to 12.01 divided by, and let's add those together. 2 carbons, 12.01 times 2 plus 1.01 times 5 plus 14.01 plus 16.00. And if I did my math correctly, I would have a 59.08 on the bottom. Oops. And I shouldn't have written equals. I should have written times 100 is equal to, so 12.01 divided by 59.08 and times 100 gives me carbon Oh, you know what I didn't do? Did you see? It's a good thing we did this one. Very important. Do you see how many carbons there are here? There are 2 carbons. I was in such a rush to get through this because I felt like this is easy. I made a careless mistake. That should have been 24.02 because you have to not just have the single atom of carbon. I should have had 2 carbons because it's 2 carbons in the C2H5NO. There are 2 carbons here. So what I should have had is 24.02 divided by 59.08 and times 100. And that gives me 40.66%. Okay. And that was actually accidentally a really good example to remind you guys, make sure that you add up all the elements for that compound, or the number of atoms in that compound when you do this. Another good example, a more simple example if you're having problems with this, if I said, what's the percentage? What is percentage of hydrogen in H2O? And so we have to do 2 H's over H2O because we have 2 hydrogens in H2O, which means it's 2.02 divided by 18.02 times 100. 2.02 divided by 18.02 times 100, and I get a majestical 11.21%. Yay. Okay. So don't forget to do that. That could be very important for the test. Okay, so that was essential skill number 1. Let me just double check. I'm still not seeing any questions, so we'll keep going. And as we go through this, I would encourage you to, because I'll do one example and then I'll do a second example, maybe pause it if you're watching this later and try to answer the question on your own, and then you can check to see if the work was right. So essential skill number 2 is determine the empirical formula of a compound. So empirical formula of compound, okay? Now this question could be asked a couple different ways. Probably one of the more popular ways is to give the percent composition, interestingly enough, first. And so let's say, let me put something together really quick. I'm trying to think of a simple one. Well, let's do It would help if I had these more on the fly. Of this coming to. All right. So we have a compound that is 39.34% sodium. And, oops. That would make it 60.66% chlorine. And so the question is, what's the formula? Okay. Now, looking at this, whenever you're given percentages, you don't know the size of the sample. And they give you, well, the percentage of the sample is 39.34%. What would it be? So the easy way to do this is if they're talking about a sample and they've just given you percentages, pretend like the percentages are actually grams. If it's 100%, it's 100 grams. So 100% is equal to 100 grams. Okay, so now the sodium is equal to 39.34 grams and the chlorine is equal to 60.66 grams. So now that you have grams, it's a lot easier and more manageable. So, and I will say this, I say this in AP Chem all the time, and pre-AP is getting you set up for AP, whether you take it that way or not. It is all about the moles. I cannot emphasize that enough. It's all about the moles. So how do you change grams into moles? Grams into moles, right? We have just finished a unit that is all about converting from one thing to another, and a lot of it goes through moles. If we're converting grams to moles, then we set up a bridge. We start with grams here, and we get the molar mass in grams here to 1 mole here, and we take whatever our given is, and we divide it by the molar mass. So for sodium, 39.34 grams, do a little bridge, 22.99 grams in 1 mole, because we're converting grams to moles. So 39.34 divided by 22.99 means that we have 1.711 moles of sodium. For the chlorine, we have 60.66 grams. And the mass of sodium is 35.45 grams and 1 mole, because we're converting to 1 mole. Remember, this is what I should have done if I had been doing this problem. Number, unit, substance. Oops, that's the amount of sodium down here. These are chlorine down here. Chlorine, chlorine, chlorine. So we're all on the same page. So 60.66 divided by 35.45. And I get, interestingly enough, 1.711 moles of chlorine. And when you do this, you need to take the largest number and divide it by the smallest number. Or if you have multiple elements, you take every number of mole and divide it by the smallest number of moles. So they're the exact same. So 1.711 moles of sodium divided by 1.711 moles of chlorine, and we get a 1-to-1 ratio of the moles of sodium. I'm going to just write that out. 1 mole of sodium to 1 mole of chlorine. So it's the formula is NaCl. Okay, so I did that with a really easy one. Let's do it with a more difficult one. Okay, we are given, and this is one, if you're watching this later, after I give you the problem, you should pause it, try to solve it, and then look at the answer. You're given 65.5% carbon. You're given 5.5% hydrogen, and you're given 29.0% oxygen, okay? And we need to figure out what the empirical formula is for this problem. So go ahead and pause now if you're watching later. If you're watching live right now, let's just solve this. So remember, if this is 100%, then it's 100 grams. So we have 65.5 grams of carbon. We have 5.5 grams of hydrogen. And we have 29.0 grams of oxygen. It's all about the moles. Let's solve for moles. 65.5 grams of carbon. Make a bridge. We have 12.01 grams of carbon on the bottom and 1 mole of carbon on top. When we solve for that, 65.5 divided by 12.01, I get 5.45 moles of carbon. Now let's look at our hydrogen. We have 5.5 grams of hydrogen. And we have 1.01 grams of hydrogen on bottom and 1 mole of hydrogen on top. So 5.5 divided by 1.01. And interestingly enough, 5.45 moles of hydrogen. That's very telling. Our last one is 29.0 grams of oxygen. 12.01 grams. Oh, good Lord. That's not the mass of oxygen. Let's try that again. 16.00 grams of oxygen and 1 mole of oxygen on top. 29.0 divided by 16.00. And as an answer, I get 1.81 moles of oxygen. And if you remember what I said, you have to divide all the numbers by the smallest number. So we'll do carbon divided by oxygen first, which is 5.45 moles of carbon over 1.81 moles of oxygen. 5.45 divided by 1.81, and I get 3.01 moles of carbon over just 1, not anything else. Sorry. 1 mole of oxygen, because when we divided it, that's what we got. So basically, when it's like this, we can just round it. It's basically 3 to 1. 3 moles of carbon to 1 mole of oxygen. Now you might say, well, how do I know when to round it and when to not? I'll get to that in a second. Let's go ahead and finish off with hydrogen and oxygen, which we pretty much already know. And then we'll get our answer and we'll go back to the rounding. So hydrogen is 5.45 moles of hydrogen over 1.81 moles of oxygen. And it's the same thing, 3.01 moles of oxygen over 1. Mr. Werner is moving too fast and not paying close enough attention to what he's doing. 3.01 moles of hydrogen to 1 mole of oxygen, which is basically equal to 3 moles hydrogen, 1 mole of oxygen. So if I write these out, because they're nice round numbers, C3H3O, and that's my answer. Easy peasy. Okay, the rounding. This is what I would say. This is pre-AP, so I'm not going to push it really hard. But if you divide them, like when you start seeing fractions or you start seeing decimals, how do you know if you should multiply that by a whole number or not? This is how you know. If you have anything that has to do with 1/2, so if it's 0.50, yes, you have to do that. If you have anything to do with thirds, so 0.33 or 0.67. If you have anything to do with fourths, 0.25, 0.50, which is what we had right here, and 0.75. And lastly, I would say anything to do with 1/5, 0.20, 0.40, 0.60, and 0.80. And so these are the numbers that I would say that you should pay attention to. These are the decimals. If it doesn't fit nicely into one of these categories, then it's probably rounding. And which also, I would say that if it's less than 0.20, like basically if it's less than 0.10, you should round down. And if it's greater than 0.90, you should round up. This is a good rule for right now. Later in AP, we'll probably adjust it a little bit, but for right now, this is just fine. We're not going to give you anything too complex. And so that's how you would find the empirical formula. That honestly is probably one of the more difficult for this. Finding percent composition, not too bad. Finding molecular formula, you're going to find is not too bad. The empirical formula is the one that has the most steps involved. And so you really need to focus your time and energy there. Okay, so let's go ahead and move on to the number 3. Number 3, molecular formula. Okay, let's say that you had done the same, you had been given this C3H3O, and they would say, what's the molecular formula of the compound if there are 110 grams per mole? If this is the molar mass of your compound, what is the molecular formula? Okay, so this is what you have to know about empirical formula versus molecular formula. The empirical formula is the reduced formula. Okay, the molecular formula is some multiple of the empirical. I'll just abbreviate empirical formula. Okay, so before we solve for the 110 grams, let me give you guys an example. C6H12O6. This is glucose. This is a molecular formula. So the question would be, what is its empirical formula? Well, remember, empirical formula is the reduced or simplified version of the molecular formula. Can 6 and 12, can they be reduced down if they're some sort of a fraction? Are they divisible by one another? Absolutely. 6 goes into 12 2 times. So it becomes 6H2O. This is the empirical formula, CH2O. The molecular formula is some multiple of the empirical formula. If I multiply all of these subscripts by 6, I get C6H12O6. So to go back to our problem here, if we have 110 grams per mole of the C3H3O, so I should probably write that over here. C3H3O is the empirical formula. It cannot be reduced down any further. We have 110 grams per mole as our molecular, or I'm sorry, the molar mass of our molecular formula. So we're wondering, what is this? So what we have to do first is find the molar mass of this. Okay, so 12.01 times 3 plus 1.01 times 3 plus 16 is equal to approximately 55. I think we'll just say 55. So 55 grams per mole. So what we have to do is take the molar mass, the molecular formula divided by the empirical formula. which is 110 grams per mole divided by 55 grams per mole. And we're going to get a multiplier. The grams per mole, those units cancel out, leaving us with a multiplier of 2. So we have C3H3O times 2 gives us C6H6O2. And this is our molecular formula. So in all honesty, I believe this molecular formula to be quite a bit easier. Usually it's just one more problem, an extension of a previous or a prior problem to get to the molecular formula. So those are our first 3 essential skills. The last essential skill that is going to probably, it's not going to give you fits, but I don't know how well you're going to remember these things. We're going to go ahead and go through it. And hopefully it makes sense to you, is the periodic trends. And I'm going to simplify it quite a bit. But I believe that it will make sense, okay? The 3 main, I should just say it, number 4, periodic trends. Okay, the 3 main periodic trends are 1, ionization energy. And honestly, this is the periodic trend we reference most frequently. This explains so many things about the atom and its bonding, and the AP comes back to ionization energies very frequently. So ionization energy. And if you remember, it is the energy required, and I'm going to abbreviate here, to remove an electron. Now, in AP, the definition changes to removing a mole of gaseous electrons from, or I'm sorry, remove a mole of electrons from a mole of gaseous atoms. For right now, though, let's just go with the same energy required to remove an electron. Energy required, that means it takes energy to make this happen. Energy has to come from the outside into an atom to remove that atom, okay? It's somehow pulling it away. And as we move left to right across table, what happens to the ionization energy? And you would say, well, hey, it increases. And I would say, that's fantastic. Can you explain why? You would need to say that as you move left to right across the table, the effective nuclear charge increases. Okay? We are increasing, and so basically that gives me the what happens, why. Like what does that mean? This is the part that's the most important. So basically it's like it's oftentimes described as, let's say, a string of pearls, like they one connects to the other. So 1, increased number of protons. Okay. 2, it increases the positive charge. 3, resulting in greater attraction or pull on the valence electrons, thus making it more difficult to remove. Okay. And the way that is asked most frequently in AP would be to compare 2 atoms. So let's compare sodium versus chlorine. Okay, which one has a higher ionization energy? We're going to abbreviate that to IE. And so the answer is, oh, chlorine has a higher ionization energy. So, so you would say, even though they have the same number of shells, that chlorine has a higher number of protons, which means an increased positive charge. So it's a greater attraction or pull on valence electrons, thus making it more difficult to remove. It has a higher effective nuclear charge. Okay. This is, and it sounds like a lot, but this is your explanation right here. Like all of that, basically talking about it, comparing the two atoms. Okay. That's what ionization energy is. Very important to be able to go back through that and explain when you're comparing atoms, when you're comparing these things of why one thing is more than another. And I'm hoping that this is registering with you guys that these things are, that's why the ionization energy is because of the protons. The effective nuclear charge is being increased. What is nuclear charge? Nuclear charge is basically the number of protons you have. Effective nuclear charge is because there are electrons in between the nucleus and the valence electrons. They have an effect, that they are interfering with that nuclear charge. And so now it's not just nuclear charge, it's the effective nuclear charge. Okay, so that was ionization energy. Oh, sorry. What if you're moving down the periodic table? So still for ionization energy, what if you're moving down the table? Okay, in this situation, the second very important force, or not force, I'm sorry. The second important explanation, or the second important factor is what I should say, is about shielding. So shielding is the blocking of the nucleus by energy levels. Okay, so the blocking of the nucleus by energy levels. You could look at it easily enough if you're looking at, let's say, the difference between sodium versus rubidium, and which one has a lower ionization energy. Okay, so you might say, to start off with, even though, it's a great way to start, even though they both have one valence electron, one, the valence electron, experiences greater shielding in rubidium because it has, what does rubidium have? wait, 1, 2, 3, 4, 5 energy levels because it has 5 energy levels, or you could say shells. Shells. To only sodium has 3. For sodium. Thus greater shielding. Shielding, making it easier to remove the electron. Wow. I need to stop trying to write sentences on this bamboo tablet. My handwriting is bad enough, but on this bamboo tablet it's just horrific. Okay. So hopefully that gives you some idea of when you're talking about this, what these things mean and how you're going to need to respond on the test. So that's ionization energy. So let's move through the other two a little bit more quickly because they're just annoying. Sorry. So the second trend we're going to talk about electronegativity. And electronegativity and ionization energy have the same trend, but there is one glaring difference. Because electronegativity is the ability to attract electrons. Because of that, noble gases essentially have no electronegativity. Oh, oy vey. Noble gases are essentially 0 electronegativity. I'm going to abbreviate it here. Okay? So you remember this because of the, well, hey, put these in order, and they would have like neon would be in there, and let's just go straight across. Neon and oxygen and lithium and nitrogen and carbon. Like put these in order of least to greatest. And so a lot of people messed up and put neon as the greatest, when in fact it should have been least, neon, because it is a noble gas. There we go. So least to greatest. Moving across the periodic table, left to right. Okay. So, and this one, again, if you're going to talk about this stuff, left to right across the table, you're going to have the same rationale talking about effective nuclear charge. As you move left to right across the table, the number of protons increases, which increases the positive charge, which increases the ability to attract electrons, right? A greater effective nuclear charge. The noble gases are the exception because they have a full outer shell. They've fulfilled the octet rule, so they will not attract an additional electron. That's why they're so low. Moving top to bottom, it decreases, right, because of shielding. As you move down the table, the nucleus is, or I should say, the valence electrons are shielded from the nucleus by additional energy levels, by additional shells. These block that nuclear charge, so reducing the pull. The shielding, the shielding effect makes it more difficult to attract electrons, so thus decreasing electronegativity. And the last one that, in my opinion, is the easiest, and it's just the opposite of the other two, is atomic radius. Okay. There is a tricky part. As we move left to right across the table, definitely effective nuclear charge increases. Okay. And so you would say that because the electrons are being added to the same energy level, okay, they're being added to this. So as you move left to right, electrons added to same energy level. There's no real increase in size. But what is happening is that because protons are being added, all the other things that go with this, right? So effective nuclear charge increases. You know what? And it's a lot easier if I just do this is effective nuclear charge, because Z is, oy vey. Z is nuclear charge, and the EFF is effective. So the effective nuclear charge increases, right? The number of protons increases. As the number of protons increase, the positive charge increases, which increases the pull or the attraction for the outer electrons. So even though the electrons are being added to the same energy level, it's being pulled in. It's making the atom smaller. The radius is decreasing because of this increase in effective nuclear charge. So as you move left to right across the table, the atomic radius decreases. As you move top to bottom, it increases. And you could say shielding, or in this particular case, you could just say, hey, you're adding energy levels, you're adding rings. It's just, you're making it bigger, which makes a lot of sense. Okay. Adding energy levels, so just making it, making it bigger. I don't know. All right. All right. I kind of thought there would be questions at some point. So I had not planned anything else, and there have been no questions, absolutely zero questions. So I don't know what's going on. So I think what I'm going to start doing for these, and there are usually not very many questions, I'm going to start planning a more lecture style review and see, because I want to see, people are watching this on YouTube. I want to watch the metrics, watch the analytics, and see what's happening. Because if most people are using this as a review later, like the night before, then I'm going to start doing other things in this. Like I'm going to use little YouTube videos, or I'm going to use animations, things that I had not planned on in the past, because I thought I would just be working out problems for you guys. So maybe we'll plan to do that in the future. But again, since there's nobody else on here, this has been going on for almost 45 minutes, which I think is a good amount of time. But please feel free to come in and talk to me before school or after school. I'm only going to be there, or plus in lunch as well, sorry. Tomorrow during lunch, I'm actually have to go to a meeting at 12:50, so I'll be there during plus, but not so much during lunch. After school, I'll be there for a half an hour. You can always catch me before school on Wednesday as well. But of course, the key there is that the pre-AP test is before school, during plus lunch, or after school. So any one of those times would be fine. All right. So I hope you guys are finding this useful, and I will just see you in class. Bye.